Hello, this is Dr. K. Welcome to Module 9 on Component Level Design. This module is roughly based on Chapter 14 of Software Engineering, a Practitioner's Approach by Roger Pressman and Bruce Maxim. As you're going to see, a good part of the module is dedicated to the software engineering design principles put forth by Robert Martin. In the first part of this module, we're going to look at the design principles that are discussed in Pressman. However, you should know that these principles are taken from a paper entitled Design Principles and Design Patterns that was written by Robert Martin. It's available at www.objectmentor.com, and we're going to be referring to it a lot. Before we get into the design principles, let's look at the Object Management Group's description of what a component is. In case you don't know, the Object Management Group, or OMG, is one of the most popular standards groups in technology. It sets the standards for things like Corba and UML. Okay, in this definition of component, we see terms like modular, deployable, and replaceable. They all seem to suggest that a component can exist independently of any system that it's used in. This notion is strengthened by the fact that its implementation is hidden, while its interfaces are publicly visible. An interface provides the user of a component with all the essential information they need to use the component in their system. We'll see this reflected in one of the design principles later in this video. Here are two different but related views on components, depending on whether you're using an object-oriented language or a non-object-oriented language. In the OO view, a component is simply a set of collaborating classes. Note that a component may be as simple as a single class. However, the OO definition seems to be more in line with the idea that a component consists of a package and all the classes it contains. The definition is not necessarily clear-cut, but the key things to remember are those in the conventional view. A component has an interface that allows a user to use it in their system, and a component has an implementation that allows it to run on the user's system. In his paper, Design Principles and Design Patterns, Robert Martin begins by asking the question, what goes wrong with software? Now, this is a pretty big question, and we've talked about it before when we talked about why software deteriorates. And if I give you just 5 seconds, you should be able to tell me why software deteriorates with a one-word answer. 5 seconds starting now. Ready? The one-word answer is change. Software has to change due to enhancements, adaptations, and bug fixes, among other things. But why? Why should those changes make software deteriorate? One answer is that maybe the software was not designed to accommodate those changes. Or maybe it was designed to accommodate the changes, but maybe the developers that made those changes ignored the initial design for a variety of reasons. For example, maybe it was easier or faster to make the changes without preserving the original design. Or maybe the developers were not as familiar with the original design as the original developers were. For whatever reason, it's typically the design that begins to deteriorate. Martin lists some symptoms of rotting design. First, the software becomes rigid rather than flexible. Software that is rigid is software that is difficult to change. Next, the software becomes fragile. This is related to rigidity. It means that the software tends to break when someone tries to change it. In other words, changes tend to introduce bugs into the software. Software that has immobility is software that is difficult to reuse in another system or even in different parts of the same system. Finally, software with more viscosity means that it's easier to hack the software to get it to do what you want than it is to maintain the design of the software. I think Martin's ideas regarding the relationship between change and design are so important that I'm quoting them here fully. He says, "The immediate cause of the degradation of design is well understood. The requirements have been changing in ways that the initial design did not anticipate. Often, these changes need to be made quickly and may be made by engineers who are not familiar with the original design philosophy. So, though the change to the design works, it somehow validates the original design. Bit by bit, as the changes continue to pour in, these violations accumulate until malignancy sets in." And this part is also important because here he talks about taking responsibility for software deterioration. He says, "However, we cannot blame the drifting of the requirements for the degradation of the design. We, as software engineers, know full well that requirements change. Indeed, most of us realize that the requirements document is the most volatile document in the project. If our designs are failing due to the constant range of changing requirements, it's our designs that are at fault." Okay, so the problem is not changing requirements. Those are just a reality that we have to live with. The problem is with the design. So how does Martin propose to fix the problem? Well, he gets even more specific. He says that the cause of software rot can be traced back to improper dependencies between modules. And the way to cure software rot is to manage those dependencies using basic design principles. Martin gives 4 principles of object-oriented class design to help us with designing our components: the open-closed principle, the Liskov substitution principle, the dependency inversion principle, and the interface segregation principle. Now let's find out what each of these principles mean and how we can apply them. The first principle, and according to Martin the most important, is the open-closed principle. It says that a module should be open for extension, but closed for modification. Here's what Martin says about it. Of all the principles in object-oriented design, this is the most important. We should write our modules so that they can be extended without requiring them to be modified. In other words, we want to be able to change what the modules do without changing the source code of the modules. All right, well, just how are we going to achieve this? Let's look at an example. Here we have a modem class with a logon method. The modem class uses an enumeration type to determine what kind of modem it's logging on with. Based on that information, it will use the logon sequence appropriate for that modem. For example, if it's a Hayes modem, it will use a Hayes modem logon sequence. If it's a courier modem, it will use the courier modem logon sequence, and so on. As a result, it has this complicated conditional code in the logon method. And if you want to add another kind of modem to the application, you have to modify the logon method in the modem class. Unfortunately, this type of design is going to violate the open-close principle. A solution to this is to make modem an abstract class and make the specific kinds of modems concrete classes that inherit from the modem class. Then, each specific modem can implement its own logon method that behaves appropriately for its type. Now, if you want to add another type of modem to your application, all you have to do is extend the abstract modem class. You do not have to modify existing code. This is the whole point of the open-close principle. Now, the redesign that you see here is actually a common refactoring. If I give you 10 seconds to pause the video, can you tell me what the name of this refactoring is? Okay, the answer is replace conditional with polymorphism. From Fowler's refactoring website, he gives the following problem for this refactoring. You have a conditional that chooses different behavior depending on the type of an object. And for that problem, he gives the following solution. Move each leg of the conditional to an overriding method in a subclass and make the original method abstract. Here are some final thoughts on the open-close principle. Martin says that abstraction is the key to this principle. In our example, we made the modem class abstract and we were able to extend it with new functionality without modifying existing code. And that's the key point. As Martin says, if you don't have to change working code, you aren't likely to break it.